Math 1332, Chapter 2, Set Theory, Section 5, Infinite Sets, Video 4. Proof the set A equals a set of all x's such that x is a real number and x's between 0 and 1 is uncountable. Disclaimer. This video won't be assessed on homework or test. This is purely informational. But if you followed me so far, I challenge you, I invite you to watch this video and see if you can follow it, because a lot of people have this misconception that I can't do math. I can't understand math. I have the conception that anyone can understand a lot more math than they think that they can. So the purpose of this video is not just to prove the claim that I made in the previous video, but to convince you that you are capable of following a train of thought that leads to a conclusion as abstract as this set is uncountable. All right, now I'm going to leave out some of the rigor because of the level of this class, but I'll try to maintain the gist of this proof. And to be honest with you, in upper level math, we're talking junior, senior level, and then graduate math, it's all about proofs. Almost everything is about proof this, and conjecture things and prove them. But we're going to prove that this set is uncountable. Now, we're going to use a proof technique called proof by contradiction. Now, what does that mean? What that means is we assume the opposite is true and show that it leads to something that's impossible. And anytime you assume something is true and it leads to a contradiction, meaning something that can't happen, that means your original assumption had to be false. So we're going to start by assume A is actually countable. At the end, we're going to run into a contradiction, but everything will have followed logically from our assumption. And since the logic is good, but the conclusion is bad, that means the assumption was wrong. All right, so assume A is actually countable. Then we can list all the elements of A in some order where every element of A is accounted for. In other words, we can put A in one-to-one correspondence with the natural numbers. You notice I misspelled correspondence again. For some reason, when I type that word, I always leave out that in there. All right, so let's assume that we can do this. And also recall that real numbers represent all possible decimals. So we can represent the elements of A using just decimals. So let's say that the first element in A, we'll call it A1, lowercase a1. Let's say the first element in A is some decimal. Now, being between 0 and 1, all of these numbers will start with 0 point, with the exception of 1 itself. So we can just assume that it starts with 0, but if you want to, we can put 1.00 there forever. Now, the elements of set A are all decimals, and it's all possible decimals. So either they end, they repeat, or they do neither. So for example, maybe the first element of A is 1/2, which we could write as 0.5. But I'm going to write it as 0.500000 forever. Okay, so let's just say that that's the first number. It could be any number, but let's say it's that one. Let's say the second number is let's do 1/3, which is 3 forever. And again, why does it have to be this one? Well, it doesn't have to. I could really be super generic here and use variables to represent the individual digits of the decimal, but then it's going to get really messy. So we'll just assume that we have a particular ordering already, and it starts this way. Let's make the third one something completely arbitrary. We'll say it's 0.011371, just some random collection of digits in no particular order. Let's put a couple more random ones. Let's say this one is 0.73 and then just a bunch of sevens. And we'll do one more. Let's say this one is, well, let's use 1, which is the same as 1.000. So we're assuming that every element of A is in this list somewhere. Because that's what it means to be countable. I can count my elements. I can put them in an order, first, second, third, fourth, fifth, and every single number in my list will be there somewhere. Now, where's the contradiction? Well, we're about to find it. If I can get this text box. In fact, I'm going to pause this and type what I just wrote up there because it's pretty sloppy. All right, I cleaned it up a little bit. I moved my list of elements off to the left, and I went ahead and typed that since A is countable, based on our assumption, every element of A must appear in this list at some point. So what's the contradiction? Well, we're going to build an element in A that can't be in this list. Now, how are we going to do that? I'll show you. We're going to define a number, and we'll call it X in the following way. Now, I'll illustrate this. It's a little tricky to put in words. The j'th digit in the decimal representation, of X is equal to the j'th digit of the j'th term subtracted from 9. Okay, so that it's really messy, and unfortunately I can't think of a better way to say this, but here's how we're going to define X. Oops, don't want that. I want that to be black, please. We're going to define X as a decimal. We'll start it with a 0. Now, starting with a 0 guarantees that X is supposed to be in this set, because this is all the decimals between 0 and 1. So starting with 0 is going to be there. For the first decimal digit, what we're going to do is we're going to do the first number in the list, and we're going to subtract it from 9. That's all this is saying. For the first number of our number that we're creating, we're going to the first number in the list and subtracting its first digit from 9. 9 minus 5 is 4. By the way, subtracting it from 9 guarantees it will be different, because there's only one number you can subtract from 9 and get the same results, and that's 4.5. But these digits are digits. They're not decimals in their own rights, so I'm never going to get the same number. For the second digit in X, we're going to go to the second number in the list and look at its second decimal and subtract it from 9. 9 minus 3 is 6. So it can't be 3 because I subtracted it from 9. For the third decimal digit of X, we're going to go to the third number in the list and take its third decimal digit and subtract it from 9. 9 minus 1 is 8. Again, by subtracting a digit from 9, it's going to create a different digit. And let's keep going. For the fourth decimal digit of X, let's go to the fourth number in the list, go to its fourth digit and subtract it from 9. 9 minus 7 is 2. And then for the fifth digit in X, go to the fifth number in the list, go to its fifth decimal digit, subtract it from 9. 9 minus 0 is 9. And because this list goes forever, so will this. So we've just created a new decimal. We called it X, and we created it by subtracting certain numbers from 9. So we know two things about this X. Number one, the value of X must be in A. Why? It's a real number, and it's between 0 and 1. But X cannot possibly be in this list. Why can't it be in the list? Well, it can't match the first number because it doesn't have the same first digit. It can't match the second number because it doesn't have the same second digit. It can't match the third number because it doesn't have the same third digit. It can't match the fourth number because it doesn't have the same fourth digit. It can't match the fifth number because it doesn't have the same fifth digit, and so on and so on and so on. There's a more formal way to write that. You could say that the jth digit in X is different than the jth digit in AJ, but like I said, I'm trying not to get this too complicated. If you can follow the setup of X, the number that we created, by taking this list that we created over here, by taking this list, which granted we just put in some random order, but that's okay, because if we're countable, we can put them in some sort of order. But if you understand how we created the X and the fact that it can't match any of the numbers in the list, there's our contradiction. Because X has to be an A, but X can't be in this list. Contradicting the, quote, fact that the list contains all elements of A. I think that's off the screen. Hold on. Just a little bit. There we go. The value of X must be in A. And then again, that's because X is between 0 and 1, and A contains all the decimals between 0 and 1. But X can't be in the list for the reasons we pointed out, contradicting the fact that the list contains all the elements of A. Since we arrived at a contradiction, our assumption must be false. As I say, I know I've got some typos in there. Our assumption was that A was countable, therefore A is uncountable. Again, if you followed that, great. If you followed even a little bit of it, wonderful. If you followed none of it, it's not the end of the world, because this was an extension to what we did in the previous videos. What I'm going to assess you on is, do you know the definitions of countable and uncountable? And do you know how to show a set as countable by putting it in one-to-one correspondence with the natural numbers? One last comment. Because this is now proven to be uncountable, any larger set that contains it must also be uncountable, which means the real numbers are uncountable. It's the classic way of showing the real numbers are uncountable, by simply showing this little piece of it is uncountable, so the whole thing has to be uncountable as well. And that concludes the video series for chapter 2, section 5, which also concludes the videos for chapter 2.